Okay, hi. I'm going to be going through what is this? Spring 2016 right now, and this is an exam I do a lot less work with. The questions definitely get less modern. Their styles are different, and you'll see that some of them are completely unrelated to the what's going to be on our exam. But we'll still go through it, and hopefully I won't make any of the mistakes I made when I took this exam last on my own. So let's go. And immediately, question one, we see an example of, something that definitely will not be on our exam. They're just asking for a gradient, so we'll give them a gradient. We need fx and fy. Well, we can find fx. That's just going to be y minus 2 e to the x, and our fy is going to be e to the x plus 3. And they want it at 0, 0. So we'll put it at 0, 0. Plugging in 0 for x and y, we get negative 2 times 1. And for fy, we get 4. So negative 2 comma 4 is our answer. Okay, according to the second derivative test, the critical points of this function are blah, blah, blah. Again, not exam 1 material in any way, but we can do it. We know that for the second derivative test, we need an fx and an that's supposed to be a y, fy, and then we need a matrix composed of fxx, fxy, fyx, and fyy, and that these guys should be equal. Okay, so our fxx is going to be 2xy cubed minus y, and our fy is going to be 3x squared y squared minus x squared plus 2y. Okay, so things are getting a little complicated, but we can go in and find, oh God, I absolutely hate this question. We can go in and find, no, you know what, this question has nothing to do with our exam material, and it's way harder than most of the second derivative test questions that they ask, and I really, really don't feel like finding the points for this, even though it ends up being like 0, 0, and 1, negative 1, whatever. And you can actually, I've never found the third point for this. You can run these two through, and you find the answer, and I'm pretty sure it's something like that. But yeah, I'm not about to do that. Okay, question 3. The maximum value for this function on this constraint, they don't make it really that specific, but here's our f and here's our g, and so we know that we're using, sorry, the screen's dark. We know that we're using Lagrange multipliers for this, and so we know that we need an fx, an fy, and that these are equal to gx lambda and gy lambda. So let's go compute those. So fx is going to be 4x minus 2, y minus 1, and then that's going to be equal to 2x minus 2 lambda. And then also this is squared. Our fy is going to be 4x minus 2 squared, y minus 1, and that's going to be equal to 2y minus 1 lambda. So we can cancel a bunch of stuff out. We can cancel all these factors, 2's in there, and we can cancel this x component and this, that component right there. And what we end up with, if I just make everything a little bit prettier, are two nice relations. And since they're both equal to lambda, it doesn't matter what lambda is. Lambda is just there to make things equal. We can set them equal to each other. 2y minus 1 squared equals 2x minus 2 squared. We can divide everything by 2, take the square root of everything, and add 1. Y equals x minus 1. So now that we have this explicit kind of relation in here, we can go up into our constraint, like we always do, and replace every single y we find with an x minus 1. So we're going to get x minus 2 squared plus x minus 2 squared equals 2. And then, this is the same thing as 2x minus 2 squared. And we can actually divide everything by 2. And we can take the square root of everything. And I know it's plus or minus 1, but for these questions, it's fine. And we're going to add 2. So x is equal to 3. And since we know that y is x minus 1, we know that y is equal to 2. So going back up here, we can now, sorry, that's hard to read. Now that we have these two, we can go plug back into our f of xy and get a real answer out of this thing. So 3 minus 2 squared, 2 minus 1 squared, that's just 2. And there we go. Okay, number 4, this is not a very common type of question, or at least they don't ask questions in this format very often. So I wouldn't expect to see this kind of thing, and it's also not particularly exam 2 material anymore, but we can still do it. So sine x over y, we know that, and we're looking for some absolute maxes and mins. We know that as x approaches 0, sine of x will also approach 0, and we know that as y approaches 0, really bad stuff happens. Depending on which direction you approach from, the function will either approach positive infinity or negative infinity, which is no good. So we want to stay away from 0. So any statement up here that says something about the function being defined or having an absolute max for y equals 0 is very, very bad. So that's pretty much only number 1, which the function, its domain of definition would include y equals 0, and so that's no good. So let's see. The function has an absolute max or min on the domain given by y is greater than 0. Well, that's also bad because we're still, all we care about is approaching 0, and y is greater than 0 still gets infinitely close to 0. So we're not happy with that either, and this one we're unhappy with for the same reason. Let's see. Function has an absolute max or min, the domain given by. Yeah, so, sorry, I was trying to think through these, but there can only be one answer now. Actually, there could be another answer, but you know how these things go, it's never none of them. Because both of our endpoints are defined for both of these, and we got no asymptote behavior, these two are good, and we're happy. Okay, we've got what looks to be a polar integral going on here. So let's give our function a graph. Well, this disk is going to be x minus 1 squared plus y squared equals 1. So the disk with radius 1, that's 1 unit to the right of the origin. But we can simplify this. We don't have to use that disk. If we take a look, our integral just cares about y. So what we can do is move our disk to the origin, and we just moved it. We moved the disk without changing any of its relationships to any y values. There's still an equal amount of area at each y value. So we can pull that little trick off, and that'll simplify things for us, because when we set up our integral dr d theta, with an r in here, this y is going to become sine of theta. And we see that we want all of the area above the x-axis. Well, we know that that's going to be for theta running from 0 to pi, and we know that r runs from 0 to 1. So now we can just evaluate. R cubed over 3 sine theta on 0 to 1 is going to be sine theta over 3. Taking the antiderivative, we're going to get negative cosine of theta over 3 on 0 to pi. which is going to be 1/3, and this is going to be -1/3. So overall, answer's 2/3. Okay, we've got a triangle with some vertices, and we are just setting up an integral in rectangular coordinates with an arbitrary function in it, and we see that we're always doing dy dx, so that's important to note. Our triangle has vertices 0, 4, 1, 0, and 0, -2. So make that triangle in there, and we see that if we're taking the derivative with respect to y first, we're going to draw a line parallel to the y-axis, and we see that that intersects the line y equals 2x minus 2 first, and leaves the region at the line y equals 4 minus 4x. And so if we go in here, I bet we can knock some of these choices out. We want our lower bound to be 2x minus 2. That's not that. Neither is that. Neither is that. That's good. And that's bad. So we already have our answer, but let's make sure it also agrees with everything else. 4 minus 4x, and x running from 0 to 1. Yep, we agree with all that, so B it is. Okay, 7, we're finding the area of the part of z equals 1 plus x plus 2/3 y to the 3/2. It lies above the square with vertices, blah, blah, blah. So let's give it a graph. It's the unit square, I guess you could say. So there's our region, and it's a surface area integral. This question is not on the exam, apparently. No surface area questions, but still we're going to do it. So surface area, your integrand will be the sum of the square root of the sum of the squares of the derivatives of the partial derivatives of your function up here, which is a lot less scary than it sounds, because really all it's going to be is root fx squared plus fy squared plus 1. There's always that little plus 1 on there. So computing, fx is going to be 1, so we're going to get 1 squared, plus fy is going to be root y, so that's just going to, that's going to become y. And then we got to add 1. So root y plus 2. And then we can integrate. Dy dx, 0 to 1, 0 to 1, doesn't matter the order, and our bounds are equal. And so integrating with respect to y, we're going to get 2/3 y plus 2 to the 3/2, evaluated on 0 to 1, which is going to be 2/3 2 to the 3/2, and this is going to be 2/3 3 to the 3/2. And then evaluating on 0 to 1 for x, we'll just multiply everything by 1. So we're going to skip that step. And we see that we have 2/3 3 to the 3/2 minus 2 to the 3/2, which is in fact one of our answer choices. Okay, next we are doing a cylindrical integral, it looks like. And this is a fun one. So they're giving us this equation, which is a square on the YZ plane, which is kind of no good. And what I ended up, it's just hard. It's hard to visualize. It's hard to draw, and it's not very fun. So what I'm going to do is replace every instance of z. Sorry, it's raining on my iPad right now. Gotta fix that. Every instance of z with x. So we're going to have triple integral of x dz r dr d theta, and that makes it a lot easier for us to take a look at. So we're going to be bounded. Well, let's rewrite this. Y squared plus x squared equals 4. Z equals 0, because now all of our x's are z's, and y equals z. So this works out really nicely, because we see that r, this is r squared equals 4, so r equals 2. R is running between 0 and 2. Z is running between 0 and y, so we can put that in there. R is running between 0 and 2, and we're in the first octant here, so theta is going to be 0 to pi over 4. And by 4, I mean 2. So let's integrate and cross my fingers that you know, because whenever you do all this kind of weirdness, there's a pretty good chance for error. So hopefully we survive though. So we're going to get xz evaluated on 0y. Oh, okay. There's a mistake. Let's quickly fix that. This y up here is actually r sine theta. Let's not forget r sine theta. So that's going to be r sine theta. Oh, and this x is going to be r cosine theta. Glad we caught that. R cosine theta. So r squared sine theta cosine theta. And this is, of course, going to be 0. And so now we have the integral from 0 to 2 to worry about of r cubed, because remember we've still got this r hiding in here, sine theta cosine theta dr. So that's going to be r to the 4th over 4 evaluated on 0 to 2, which is just going to be 4. So 4 sine theta cosine theta evaluated on 0 to pi over 2 d theta. Well, we know that 2 sine theta cosine theta is sine 2 theta. So this is the same thing as the integral from 0 to pi over 2 of 2 sine 2 theta d theta. And if we integrate, we're going to get negative cosine of 2 theta. That looks like cosine squared. Negative cosine of 2 theta evaluated on 0 to pi over 2, which is going to be 1 minus 1, which is 2. And thank God, because that's the right answer, and I really don't feel like re-recording this stuff right now. Okay, number 9. Which of the following integrals represents the volume of the solid enclosed by these guys? Okay, so let's immediately stop and so let's replace some things. So looks like we're dealing with cylindrical. All of our integrals are in cylindrical coordinates, even though we have an x plus y plus z all squared, which we would think would be rho, but in this case it's not. So we know that we can replace that with an r, so z equals r, and we can solve this guy for z. That's going to be z squared equals 2 minus r squared, so z is root 2 minus r squared. And we also know that because we have this factor here when r is equal to 0, this guy will be on top of this guy. So this is our upper bound, and we see that here. So any integrals with respect to z, all these inner ones, let's make sure that they align with what we've found. Well, this guy doesn't, and this guy doesn't, and all three of these guys do. So we still got 3 to choose from, but we just knocked a couple answer choices right out off the bat. So now let's go take a look at what our r values are running from. So if we set these guys equal to each other, we're going to get r equals root 2 minus r squared, squaring everything. R squared equals 2 minus r squared. So this is 2r squared equals 2, r equals 1. And so we know that r is running between 0 and 1. So here's our only answer choice. These other ones, no good. Okay, we're finding the volume of the solid enclosed by spherical coordinates. Sounds good. Enclosed by the sphere with radius 1 and the sphere with radius 2. So rho is 1, rho is 2, and this guy. And if you remember correctly, this guy forms a cone um, that makes an angle of pi over 4 um, with respect to both the xy plane and the z-axis. So we got this guy. So we're taking, if we take a look at this, if we have the xy plane sitting down here and we have the z-axis, we have this cone coming up, and we have the sphere with radius 1 and sphere with radius 2. We're looking for this area inside there. So setting up our integrals, d rho d phi d theta, we see that well, theta, we're not dependent on theta anywhere in here. Theta is just going to go all the way around, so 2 pi, and we know that rho runs from 1 to 2. We just established that up here, and we know that phi runs from 0 to pi over 4, which we saw graphically from drawing our cone out. And you can do it with formulas, but you know, we're good without. And we know that there are basic ingredients we got to add here. We got to add a rho squared sine phi, and now we can integrate. So rho cubed over 3 evaluated on 1 and 2 is going to be 8 over 3, and this is going to be 1 over 3. So 7/3 sine phi evaluated on 0 to pi over 4 d phi is going to be negative 7 over 3 cosine phi evaluated on 0 to pi over 4, which is going to be negative 7 over 3 root 2 over 2 minus 1. And then we can see out here that we're multiplying by 2 pi. That's our final little guy waiting out there for us. So we're going to have negative 14 over 3 pi root 2 over 2 minus 1. And you might be thinking, oh no, look, we got a negative volume. What's going on there? But no, it's actually a positive. Oh, yeah, no, we're fine. What they did in this answer choice is just distributed this negative sign in and got that. So there we go. Okay, the gradient vector field Weistra equation. We got to identify this guy. This kind of question comes up sometimes. This could be on the exam. But what I like to do is look at the axis behavior. So we see as we increase along the x-axis for y is equal to 0, we're flowing away from the origin. Same thing over here. And on the y-axis, we're flowing towards the origin. And remember, this is a gradient vector field, so we got to take the gradients of all these guys. I'm going to avoid the E stuff. Generally, the answers, I don't know, you can go graph those gradients on your own, but the answers are not related to those. So if we take fx up here and fy, we're going to get 2x comma 2y, and over here we're going to get 2x comma negative 2y. And what I've kind of found is that if you have an axis where the axis behavior is flowing towards the origin, so in this case our y-axis, it's flowing towards itself, that means that the gradient vector for that, like the component of the gradient vector, so in this case, the y component of the gradient vector has to be negative. And we can see this because as we get more negative in y, the gradient should get more positive, flowing more and more towards that center. And so this can be our only possible answer. Okay, integrating for work. Again, this is apparently a question type that will not be on our exam, but it's still a good one to take a look at because it's covered in literally the next lesson and will be on the final. Because we've kind of already done it. So, sorry. Let's see. We've got some kind of big functions. We've got 2x sine y and then 2y, and we're on a parabola. Okay, so we can graph this thing. This is going to be going from the point 1, 1 to the point 2, 4. It's starting to rain on me. Okay, well, this is question 12, so I guess we're just going to go. Going from the point, that point to that point, we can set x equal to t and y equal to t squared for 1 is less than or equal to t is less than or equal to 2. Okay, so now we can plug in here. So 2t squared sine t, comma, nope, that's backwards, comma 2t squared. And now we got a dot with the derivative of these guys. So this guy's derivative will be 2t, and this will be 1. So 2t, 1. So we're going to get an integral from 1 to 2 of 2t sine t squared plus 4t cubed dt. And let's quickly integrate because it's actually starting to rain on me and my iPad and my jacket and everything. So let's go. We can do u sub on this. We're going to get negative cosine t squared, and then we can integrate this guy, and we're going to get t to the 4th evaluated on 1 and 2. We're going to get 16 minus cosine of 4, and we're going to get 1 minus cosine of 1. And so there's our answer, and I'm going to go inside for this final exam recording.